The section on belt drives, part of this chapter 7, you're going to apply it to your semester project, where you have to select the belt and sheaves for the punch press. And I'm saying it now, it's at the beginning of the recording. You're just going to follow the sample problem 7.2. Okay, sample problem 7.2 explains the steps to select a V belt. It's going to be a V belt, the one that you're going to use with your punch press. Okay, so and the belt transmission is in series with a gear reducer, and I'm going to discuss how to select the transmission ratio of the two to accomplish the desired total transmission ratio. Here are photographs of belt transmissions. This one used for a column or a drill press, and the way it's configured right now, it's a reducer, so the pulley is a smaller one. The input pulley on the motor shaft is smaller than the one on the spindle shaft. These are compound pulleys, or sheaves, called sheaves. The belt is V belt. And you get minimum transmission ratio by engaging or moving the belt on the smallest sheave, and will be the biggest on the spindle axis. Notice that for that purpose you need to loosen the belt, so you there is a bolt here and should be one on the other side. You untighten it and you push the motor towards the spindle. Center distance reduced, and you can move the belt. When the belt is on the top sheave, which is bigger than the spindle sheave, you achieve increasing. Most of the belts are used as gear reducers, or maybe transmission ratio 1:1. This configuration on the top sheave is an increaser used with small size drill bits. In order to achieve the desired cutting speed for that small diameter, you need high RPM. This one, it's a relatively low resolution, but you can see the components. So there's a two-stage belt transmission, belt reducer, apparently of a pump jack. This is the prime mover. Not certain if it's not an engine, it appears to be a radiator. And the first stage, it's high RPM of the high linear speed of the belt. The belt is small size and appears to be two of them. Here are multiple belts, and your thicker ones, bigger cross section. Okay. So from the chapter, I'm going to emphasize the V belt part. There is a section that reviews concepts on tangential velocity. Tangential velocity on a circle is called the pitch circle, is the linear velocity of the chain or the belt. So for a chain transmission, the pitch circle will be the circle through the center of the pins, and when the chain is outside of the sprocket, it moves on a straight line, and again, tangential velocity is the linear velocity of the chain. For the synchronous belts, the pitch circle is outside of the major diameter of the sprocket. For V belts, it's towards outside, and it's where the reinforcements, the cords, either metal or rope, so wire or rope cords to increase stiff or strength, tensile strength of the belt. Chain, in operation, there's a taut side of the chain, and the other one is loose. For belts, you'd have to have an initial pre-tension, and as the belt transmits power, the taut side tension is increased, the loose side loses tension, but is never going to go to zero. Okay, so things that you know from dynamics: how to calculate tangential velocity when you know radius and angular velocity. They are listed here, and concepts of like Peach circle. We are familiar with similar term used in gears. For any type of belt, including flat belts, which historically have been the first one that were introduced and used in practice, made of leather, of ox skin, and stitched together. And flat belts are still used, as well as the round belts. They use like O-rings. I've seen those in applications like VCRs. They have the ability of slipping if there's an overload, and it protects more sensitive components of the transmission by allowing the peak torque to be lost through friction and the slip of the belt. Anyway, so we recognize here the center distance. We recognize the angles of wrap and the length of wrap, and we recognize the belt span, the free length of the belt, noted D, and they're the two are equal length. Evidently, if transmission ratio is 1:1, the pitch diameters of the input and output sheaves are equal, then the angle of wrap is 180 degrees. This angle of wrap, you want to limit it to no less than 120 degrees. Okay, so calculations of the slope angle phi allows us to calculate the angles of wrap, and using the angle in radian, you can calculate the length of wrap. Total belt or chain perimeter length, it's going to be twice the belt span times the length of wrap, and it's this equation here. In terms of type of belts, belt drives, I said that the most common ones are the V belts, and the die cut or a cog type. It's a V belt with grooves. I remember my father's first car was using V belts to drive the water pump and the alternator, and the way they were failing is by developing cracks from the inside to like radial sort of, and you can tell that you prevent that from happening by having these controlled features, the cuts, the cog to the belt. Which allows for the angle of wrap to be, or rather the radius of the smaller sheave to be less than for a regular V belt. So more compact arrangements. And again, remember I mentioned the cracks. So these anticipate or prevent the cracks from developing by localizing the flexure of the belt in a regular fashion. The V-band and the poly-rib belt, they are like multiple belts in parallel. The poly-rib type is, you can see the triangular shape. And then we have the double V-belt. These are used for applications where you have sheaves that are driven either on the inside or outside of the belt. And then there's the synchronous belt as a separate section of this chapter. I'm not going to emphasize it on synchronous belts. Okay. The The groove angle is standardized. You can see 34 to 42 degrees. It's mentioned in the text. It provides for a wedge effect, and the torque transmitting capacity of the V-belt transmission is increased this way. And of course, it works for pulley rib or any of the, other than the synchronous belt, which is a positive transmission type. It's called synchronous belt or timing belt because there's no slip of the belt relative to the sprockets, and provides synchronism. Used in some engines to drive the camshaft. Okay, so V-belt drives, again, you have to for the project to design one. The length of the perimeter length of the belt, early equation was in a new format. And now notations used for the pitch diameters are D1 and D2. CD is the center distance, the angles of wrap, and then the equation for the belt span. Okay. In operation, the belt is subject to tensile loading, to bending as it wraps around the sheaves, and centrifugal forces. Centrifugal forces are larger as the belt move or is wrapped around the smallest of the sheaves, and you don't want that centrifugal force to be excessive and pull the belt off the sheave that is loose contact, and there's no possibility of transmitting force. Okay, so something that we used already when designing shafts, the ratio between the slack and the taut side of the belt is 5, although it can go up to 10. It's less for flat belts, and there are a number when designing a belt, V-belt transmission, a number of things to consider, like the power transmitted. Surface power is based on overloads, moderate or severe impact of presence, and as well as how extensive during the day is used the belt. You need to know center distance, belt length, and then there are some correction factors. Catalog information is given for belts running between equal diameter sheaves. You could use multiple belts. Remember the second photograph. You also need to specify the tension in the belt. These are geometries of heavy industry V-belts. The narrow section V-belts, the most common ones. This is one of these you will be selecting for a project, and light-duty fractional horsepower types. The metric sizes, they get close, and since the trapezoid are about similar, you can run a metric belt on an inch size pair of sprockets. Center distance, it has to be certain minimum value in order to be able to put the belt in place, and it doesn't or it's limited in terms of maximum length by the possibility of belt whip, which is a dynamic process that can result in the belt jumping off the sprockets. So this is the equation to follow. Belt speed is limited to 5,000 feet per minute, maximum 6,500. As well as there is a low limit, so a belt running too slow, it's subject to higher tension than so higher speed. Say I'm transmitting power at the ratio torque at ratio 1:1, no increasing, no decreasing of RPM, but If I run it between two larger size pulleys, the belt will travel at higher speed. However, for the same torque to be transmitted, tension is less for the larger size pulleys. So there are two effects that go in opposite directions. So small size pulleys, small diameter pulleys, low tangential speed, high tension in the belt. Increase the diameter, you can get to higher linear speeds, all the way to where centrifugal forces could be limiting factors and force the belt off their sheath. Temperature is also a factor. They can overheat, their slip. Belts are they have the cores, the reinforcements. They are also there's fabric, so there's the elastomer and there's fabric on the outside to provide increased wear resistance. Their life is common life of a belt transmission is 7,000 to 5,000 to 7,000. Pulleys last much longer. And then when you have belts running in parallel, you want, of course, them to be equal length, and if they are from different batches, identical, or not even, you cannot get them exactly to the micron length. But here is there's some indication of how to the match number based on the length of the belt. There's some explanation. Anyway, so 3V, 5V, and 8V will be the could be cogged if there's an X in the designation. And you start with the design power, which is the power of the prime mover, in your case the electric motor, times the service factor. Service factor is listed here. So for a punch press, you would expect 2 shifts and moderate shock. Why moderate, not heavy shock? Because of the we have the flywheel, which so look at this. You have the belt transmission, and there's the flywheel. So impact coming from the punch are shielded by the large inertia of the flywheel. Okay, so something like 1.3, 1.4. Your designer, you select, but this is the the range of values, 1.3, 1.4. This multiplies the power that you have calculated, which already has been increased over the average torque calculation, and there for a different reason, in order to accommodate larger, thicker material, stronger material, larger punch dies to be used on a press. Okay, so we have this selection chart, and if you have the design power, input power times service factor, and you have it says speed of faster shaft, that will be, say, for the punch press with a asynchronous motor, 1750, and you have like 20 horsepower. So this is the type of 3V or 3VX type of belt to use. The chapter has additional charts that allows you to find the power rating for a V belt, and this first equation indicates the various factors. So we have the basic power rating, and catalogs again lists for 1 to 1 equal sheaves, 1 to 1 transmission ratio. And for longer belts, the life is increased just because every inch of the belt on a longer belt experiences fewer number of flexing cycles in, say, 5,000 hours of operation. And then there's also the speed ratio that can result in, if it's other than 1 to 1, in an added power capacity. And then there's this factor based the angle of wrap of the sheave. However, this is not the way this equation is not the one that's used, and I mentioned sample problem 7.2. So you would see correct power rating for belt, correction for the angle of wrap and the belt length now, and so rated power is corrected through multiplication rather than addition. So a little bit confusing, but again, just to introduce concepts. And there are some charts for 3V, for 5V, and for 8V belts. And as you can see, you have the sheave diameter, the small, just because belts are mostly reducers, so you have the small sheave pitch diameter, and these are the standardized values. So 2.6, 2.75, they are not listed elsewhere. And then it continues for 3V all the way to 33.45, and then for 5V, this is a bigger gauge belt, and then for 8V the heavier duty. And then the length of the belt are also standardized. You cannot get a belt that is any length you want unless you fabricate your own. Easier to do for a flat belt that is stitched, of course. Okay, so you have here for a 3V belt, you choose the diameter. As you can see, if you go from a smaller to a larger size diameter input sheave, and this is 1750 common RPM for motors, you get a quick increase of the rated power. The dashed line, it's capturing so the solid line is for a ratio 1:1. The sheaves are equal. The dashed line, it's offset up, and it's indicative like how much added power you can get correcting for other effects like angle wrap and length of the belt. It's only for the 5V belt where this is detailed. So on the graph, so if I'm on the 1750 line, and so you would see like what you will see. So 5V, and for 1750, if I have a speed ratio of 3.38, I get the most added power for the speed ratio increase, and that's so like 2 horsepower. So let's go to 5V and 1750, and if you measure, it's about equal, yeah. So this is from here to here, or the other way, it's like 2 horsepower. Okay, so this is how they got this. This is the maximum maximum you can get as added power as function of speed ratio. Okay, so this is just for 5V, and you can use this chart if it happens that the belt that you're using for your project is a 5V type. But again, it's not valid for the other ones, for 8V or 3V. Additional effects are, so this is for the correction for speed ratio, for angle of wrap and belt length. So angle of wrap correction, as you can see, if it's 1:1, there's no correction. That is the transmission 1:1, the two sheaves are identical, the angle of wrap is 180, the coefficient is 1. And the angle of wrap correction is a less than 1 value that multiplies the power rated or rated power. And then for the length, belt length, you can, as you can see, you can have an either a reduction or an increase of the of the rated power. Okay. So same as with sheaves, you cannot get them in any size unless you design your own. You could, I mean, going back to your project, you could design the large sheave for, but the one that goes on the motor shaft, it's rational to, since the motor shaft is standardized, to use a standard off-the-shelf for cost reduction sheave. But the one that's parked with this appears to be a clutch. We never discussed this. So an actual punch press does not run continuously. You need to press a foot switch, press with the foot the switch to cycle once the press, and that happens at this level. There's a clutch, and there's a safety feature to where you need to press actually two buttons, one on the left side, one on the right side, to on some presses. I mentioned foot operated. On some presses, yes, you need to press two buttons so that both hands are clear from the pinch area of the press. Okay, so like I said, the sample problem to file is 7.2, and do the same for yours, and you might end up using two belts, as is the case here. Okay. Belt tension, you need to, in the design, need to make provisions for loosening the belt for replacement, and also tension that we looked at the drill press. There are several designs. You can use an idler. You can move away the motor. It could be with counterweights. Do research in case your project requires a belt use. I'm not going over the synchronous belt drive part. There is with any belt selection, there is information on companies' websites and catalogs, and you can call their tech advisors, and likewise for chains. Chains are rated based on their brake strength. Okay, and the cable, this new section on cable drives it wasn't in the previous diameter, rather the edition of the book, but feel free to go over the, if interested, go over the latter sections of the chapter. I know it's minute 28 of this recording, so you would have to decide how is going to the total transmission ratio, how is going to be distributed between the belt transmission and the gear transmission. Okay, and in the text, I haven't emphasized that. In the text, it says the belt transmission should be limited to up to 6:1 reduction ratio. And then for Strasbourg gears, you would also want to, typically the transmission ratio doesn't go past 4:1. I take a print screen, and I'm going to paint. So let's see. Just clear this so that you don't get okay, so we can we can try to guess the transmission ratio in this for this unit. So I'm trying to see how many times I can fit the diameter of the pinion into that of the gear. 2, 3, so more than 4, maybe 5 to 1. Okay, about 5 to 1 reduction at the gear reducer for this punch press. All right, so say I have, this is an example. This is an example where I'm assuming the motor RPM to be 1750 and the crank RPM 95. The total transmission ratio would be the transmission ratio of the belt, transmission ratio of the gear. It's written here. So what I'm doing, I'm taking the input RPM 1750 divided by 95, and this is 18.421. And then I could have theoretically, or assuming that there are friction wheels instead of gears, and then I can have any size sheave that I want. I can take the square root of this total transmission ratio and say, okay, so I can have the gear reduction and belt reduction identical. If you multiply the two, you get back the total transmission ratio. Of course, it's not possible. So you need to get these reconciled with whatever sheave sizes are available. Remember, they are not tabulated, they are part of these charts. So a 3V belt, you have the available sheave sizes listed here: 2.6, 2.75, 2.95 inches, all the way to 795. And in addition, you have these additional sizes for what you would expect to be the driven sheave. For 5V, they start at 7 and then end at 49.9 inches, and then even bigger for the 8V belts. Okay. So back to this. I could so I could try to get what do I want to do? I want to paste this, and I could make this equal to, say, the transmission ratio. So I could use let's see, actual. Let me put here actual I gear, and I can have N1 and I can have N2. Okay, and so N1, it's limited. The minimum for standard gears should be 17 or maybe 18. So N1 18, N2 now could be equal to, I have this times 18, 77. So it could be 18 and 77. So actual is going to be so I said 77 over 18, right? So that's for the gear, and then actual for the belt. And not that you couldn't adjust it, so it's not, doesn't have to be 18, could be 19, and this could be 19 and 77. Usually want them to be prime numbers, and they are 19, or 18 and 77 was were prime numbers, or maybe 22 or the 20, could be. So I'm sorry, 20, 20, 20, and maybe 7, 8. No, 7, 8 is not good because they have they're not prime numbers. Not as good. So I can have 79. Okay. then of course the difference, so actual belt, or the, from there I could get copy, not actual but rather needed I belt, I meant belt. Okay, so needed belt, that'll be this one divided by actual. Okay, so your target transmission ratio for the belt is the 4.6635. Okay, so I said could be 19 and 78. It changes, could be 19 and 76. Okay, or 74. Or maybe 80. Which one gets closer to the square root? 80, 81, 83. So you need to decide. Firstly, gears, pinions cannot be less than, unless you go with addendum modification, less than 18 teeth. Here apparently we have more than that small number. That's it's over 20. You could try to guess or count the number of teeth on both, or on other photographs of punch presses. Okay, so this could be the target number, and you go and you apply or go through the steps in sample problem 7.2. It will be RPM of the motor, power transmitted of the motor, and then the speed ratio. The speed ratio here is 1.72. Yours would be not that it's a driven shaft that is explicitly recommended, but you have the transmission ratio as it comes from this analysis. So this one would be the target transmission ratio. It's not carved in stone. So if you don't get to the exact 95 punches per minute, instead is 91, 92, 93, or going slightly above that, you're still okay. Just to let you know, the motor's RPM is not going to stay constant either. As a synchronous motor experiences loading, this slip increases and this speed goes down. It can go below, momentarily may go below 1700. Okay, so this is what I wanted to say. Part of your project, you have to draw at scale, that is, show schematics with the angle. The angle is recommended. The angle is relevant for the shaft calculation. You have to calculate the shaft of the input pinion. This shaft is supported on two ends and has an overhang, and you make abstraction of the clutch that's there. You just assume to be a sheave, so you support on two bearing. The shaft is solid was the pinion is solid was the shaft, and the large sheave is keyed to an overhanging section of the shaft. But I started saying, for the project you have to draw the pitch circles at scale as well as the mechanism at scale for somebody to have a sense of proportions of the entire unit. Okay. So I hope this helps. Thank you for watching, and we'll see you next time.